Hello, welcome to Lecture 9, and today we're looking at discrete random variables and probability distributions. We've seen from the first lecture that you can take some experimental data, in our case it was the strength of a metal, and we can process the data to produce a histogram, and the histogram shows the relative frequency density of that measured data. And we've also seen for the probability that that's a measure of the relative frequency of an outcome from a sample space. And these two things go hand in hand together. When we're measuring the strength of the metal, really what we're trying to do is to measure a probability distribution function of what its likely strength is going to be. So we're going to look in these lectures a bit more about the random variables and their probability distributions so that we can use those more broadly. So first of all, what are these variables? A discrete variable is one that is counted. It's a discrete quantity, not continuous. It's something like cars on the road. You can have 1, 2, 3, 4 cars on the road, but you can't have 3.5 cars on the road. You can't have 2.25 cars on the road. Or it could be defective pressure bursting discs in a batch. You can count those, and there's an integer number of them. It can't be a non-integer number of them. So some variables are like that, that's what their nature is. And some variables are not like that, they're continuous. For example, the electric voltage from a sensor or the hardness of steel, that's a continuous variable, like the speed at which you're travelling. And that could change anywhere between 0 and some other limit, 60 for example. Between some limits it could take any value, it has an infinite number of possible values. And today we're concentrating on discrete variables, and then the next lecture we'll look at continuous variables. So the quantity we observe in the experiment, we call that capital X, and we consider the cumulative distribution, so that's capital Fx. That's our cumulative distribution, and this is defined as the probability that our outcome is less than or equal to X. So it's all values, all possible ways in which our outcome could be less than or equal to X. So it's cumulative because it's all of those ones less than or equal to lowercase x. And that leads to the formula that the probability of our outcome being greater than A or less than or equal to B, it's equal to the difference in the cumulative distribution FB minus FA. We can prove that by looking at the intervals. Our outcome is less than or equal to A, or our outcome is greater than A but less than or equal to B. And these two are mutually exclusive. You can't be in both of those at the same time because it's less than or equal to A, or here it's greater than A. So there's no overlap between those two. So we can say the cumulative distribution of B is equal to the probability of our event outcome being less than or equal to B. And we can say that's going to be equal to the probabilities of these two mutually exclusive events, that the X is less than, outcome is less than or equal to A, and the probability that our outcome is greater than A but less than or equal to B. So those two things are mutually exclusive, and we showed in the last lecture that the probability of this is the sum of two mutually exclusive probabilities. And so we can say by our definition of the cumulative distribution, this first term here is equal to the cumulative distribution of A, and that term's the same. And now we can rearrange them to get this term on the left on its own. So the probability that our outcome is greater than A or less than or equal to B is equal to the difference in the cumulative distributions at B and A. So we'll see what that means in a moment. So the discrete random variable will have a probability associated with each possible value. So that's our outcome, and it can have a value of x1, and the probability of that is p1. It can have a value of x2, and the probability of that is p2, and so on. And for any other value of x, the probability is 0. So in terms of the probability function, the lowercase f, that's the probability function, and that is equal to pj if x equals to xj, otherwise it's equal to 0. So we can write a probability function for this discrete variable. And this is related to the cumulative distribution function that we looked on the last slide. So the cumulative distribution function is equal to the sum of the probability functions up to our limit x. So for all xj less than x, you sum up the probabilities of each of those occurrences, and that's the same as saying that you're summing the probabilities of pj from 1 to j, where j is taking us up to the value x that we're looking for. So we'll illustrate what that means in practice. The outcome is the number that a fair die turns up. So x can be either 1, 2, 3, 4, 5 or 6, and the probability of each is 1/6. So we can write our discrete probability distribution fx like this. The probability of x being 0 is 0, and it continues being 0 until we get to 1. Now our outcome can be 1, and so at that point it darts up and the probability is 1/6. But then it goes back down again and back down to 0 until we get to 2, and yes, our outcome can be equal to 2. So when x equals 2, again it darts up to our value 1/6, and then it goes back down. So this shows a probability distribution for a discrete random variable, and they're characteristic by having these spikes up and down. Now when you have the spike coming up, the line coming up, obviously this line has no width, it's only at value 1, and so we draw a little bubble on the top to show that that's the value at that point. Otherwise you might think it's undefined where you are on that line. So the dot tells us where we are at x equals 1. And from that we can calculate the cumulative distribution. So the cumulative distribution is the sum of all of these sum of all these probabilities. So as x equals 0, it starts out at 0, and it continues at 0 until we get to our first value when the outcome is equal to 1. There's a probability of that occurring, so then our cumulative distribution goes up to 1/6, and it carries on at that value until we get to 2/6, 3/6 at x equals 3, and so on. So now we are effectively integrating this or summing as we increase in x, and that's the cumulative distribution. Here's another example. Here is the probability function and the cumulative distribution function for a discrete random variable, and that's the sum of two numbers from two fair dice. Okay, so we've got these two things. The probability function, remember that tells us the probability of our outcome being a particular value of x, and the cumulative distribution function, which tells us the probability of our outcome being less than or equal to a certain value of x. So our outcome can be any number any integer from 2 to 12. This is the case that there are 6 possible outcomes, and we're drawing 2 of them, and repeats are possible. It's like yes, there is replacement, and so our total number of outcomes is n to the power k, which is 36, which we covered in the permutations and combinations lecture last week. So these are possible outcomes, and what's the probability of each one happening? Well, it's like this. You can count the number of ways in which you can get a 4, the number of ways you can get a 5, the number of ways you can get a 6, and so on, from the possible combinations of dies. So that is the discrete probability function for this occurrence, and then the cumulative will sum those up, and so once you get to 3 you add 236 to 136, once you get to 4 you add 336 to 336, and so on until you get to this point where obviously the cumulative distribution must equal 1 because there are no other possible values greater than that. So again, we can plot these. So this is our possible sum of the two dice, and this shows the probability function, and that stays at 0, and then you have a spike at 2, spike at 3, a spike at 4, and so on, and each of these probabilities has been calculated by considering the number of combinations of dice rolls that would give that value. And again, then the cumulative distribution starts at 0, and then it steps up each time as you add on the next increment until we get to 1. And so the combination of the two dice can't be greater than 12, and so every possible outcome must be 12 or less, and so the cumulative distribution at this point is equal to 1. Okay, so we've seen this result already, that the probability of our outcome being between two values a and b is equal to the difference in the cumulative distribution at those points. And so you can find that for a discrete case by just adding up the probabilities of pj for all of the x's in between a and b. Of course, like I just said, the probability of the whole sample space occurring is 1, and so if you add up all of the individual probabilities of each possible value, then that must come to 1 as well. So here we can use this result, calculate the probability of a sum of at least 4 and at most 8 from the sum of two fair dice. So that's taking the data, the probability distribution we had on the last slide, and using that. So the sum is at least 4 and at most 8. I've written that wrong in here. This should be 3 and at most 8. So we're then looking at the difference, the probability of our outcome being greater than 3, less than or equal to 8. So excuse me, that should be a 3 there. And that will be equal to the difference in the cumulative distributions between 8 and 3. And that's what we have here. At 8 it's 26/36, and here for cumulative distribution of 3 it's 3/36, and that equals 23/36. Okay, that sums up what we wanted to do to introduce the discrete random variables and their probability distributions so that you can use them now for other applications. The next lecture will follow the same idea but looking at continuous random variables. Thanks.